It's a natural log or a log rule that allows us to put 5 in front. It will make my life easier. And I will differentiate this. You don't have to differentiate that. It's the same thing. So then I have 5 over x. Good. Now, how do I find m? So this was the first step. Now, how do I find m? What is m?
5 over x.
Yes. But I'm interested in this particular m for this point.
Would it be 5 over 9?
5 over 9, exactly. 5 over 9. X is 9. All I have to do is plug it in as 5 over 9. And I got my equation. Not yet, but I'm close. Y equals y minus 5 natural log 9 equals 5 over 9 x minus 9. I distribute. So 5 9 x. 5 over 9 times 9 will be negative 5. But I have to bring this over. Plus 5 natural log 9. This is the equation of the tangent line to the graph of the given function at the point where x is 9. Very good question. Is this clear? All steps?
Yes.
Excellent. Anything else you have for me? Anything?
It's actually a question from the MyLab.
Yes, I'm ready.
Number 5.
Yes. Any particular section you want me to bring it up?
Yeah, it's like
So number 5, which section? 2.1, 2, 3?
3.
2.3. Very good. Let's take a look.
I couldn't figure out part C. Yes.
Okay. So I think I have to go back. Okay. You said 2.3 and you said problem 5. Awesome. I love it when my students do their work and they bring questions to class. That's why we are here. The demand for a new computer game can be modeled by, okay. Yeah, we just did this problem, but let's do it again for everybody.
Is that the same that we got from both number 27?
Yes. So 0, so we have, so this is in units. And this is price.
I got part A and B, but just
Say it again.
I got part A and B, but this part C, I don't know. Like
That's okay. That's okay. Recall that the total revenue is given by this. So first of all, we have to write R of x. So this is part A, which is x times 50 minus 3 natural log x. So this will be 50x minus 3x natural log x. Part B. Okay, so we first have to find. So help me here. I don't know what I'm entering. Just make
Is that
sure.
going to be 50? Oh.
So if I write it like this, is that correct? Or they want
No,
parentheses?
no.
it should be R prime of x.
No. Find R of x.
It'll be just x times 50 minus 3 ln x. No,
Yes, but
you
that's
don't have
but
to-
that's
you
the
don't have to
but
log
that's the
simplify
product.
it.
That's the product. They have to
Yes.
accept. They have to accept it. If they don't accept it, I'll have to scream at them. They have to accept it. Find the marginal revenue. So R prime of x. Good. So let's find the marginal revenue. So when I differentiate this, I look at it and see it's a polynomial, so 50. But here I have to be careful because this is the product.
It
So-
will be
Minus 3 outside, yes.
and then ln x plus x times 1 over x.
Very good. And we simplify. So we have 50 minus 3 ln x minus 3 times 1. 50 minus 3 is 47 minus 3 natural log x. I absolutely love it. 47. That's how you learn. There is no other way. Okay, so you said that 3 and then ln x does not require parentheses. Okay, so then check the answer. Okay, now let's see the last part. How many units will be sold if the price that consumers are willing to pay is $40? Which function are we using now? Notice that this sentence has nothing to do with the rate of change. It doesn't say anything. Find blah, blah, blah so that the rate of change is blah, blah, blah. No, there is no word about the derivative. So then what do?
We go to the first one and we're putting 40
Exactly.
equals to
50.
50
Yes.
minus 3 ln x.
Round to the nearest whole number. Okay. Good. So 40 equals 50 minus 3 natural log. We move this to the other side. Negative 10 equals negative 3 natural log x. Of course, we need to divide by 3. Remember, the base here is e. We don't write it. E raised to this number equals x. E raised to 10/3 equals x. And we put this in the calculator. And it was e in parentheses 10 divided by 3. Close the parenthesis, press enter. And this is in thousands. So let me copy first as x equals 28.03162. And look again, where is the book? Okay, round to the nearest whole number as needed. So I have to multiply by 1,000 and then round this to 2. So 28032. This is what I'm going to enter. Units. So 28032. Just making sure. It said here in thousands. Yes, it does. Okay, I'm checking. Good. Perfect question. Thank you. Is there anything else we need to look at?
I just have a quick question.
Yes? Anything?
You said multiply by 10?
No, by 1,000.
By 1,000?
Yes. So when we multiply by 1,000, we have to move the decimal point 3 units to the right.
Okay.
1, 2, 3. Since this is a number greater than 5 or above, I have to round this to 2.
Okay. Thank you.
Is that okay?
Yeah.
You can put a comma if you want. 20,032 units. Perfect. I hope this helps with your homework also. Great questions. Anything else? Wonderful. Okay. We are ready now to start chapter 3. I am on page 4. So for test 2, we have chapter 2 and we have chapter 3. This is a big chapter. We are talking here in chapter 3, we are going to look at applications of differentiation. In other words, you can say, but haven't we applied this already? Just today, we applied differentiation for this to find the marginal revenue. We apply differentiation for this to find the marginal profit. We've applied differentiation to find the slope. Aren't these applications? Yes. But we have even more applications of differentiation. Applications. If you want to call this chapter more, you can call it more applications of differentiation. So we're going to start with sections. I would like to combine them. I always like to combine 3.1 and 3.2. I don't know if we can accomplish both tonight. I doubt. This was so important This is way more important than anything, to discuss situations and understand what we're doing here. Awesome. Okay, so first I would like to look us to look at a graph. So let's say I have a graph. This is the graph of a function. I'm going to call it f of x. So let's look at this function and realize that at this point, if I want to draw a tangent line, the tangent would look like this. Will it have a positive slope? Is this a positive slope?
Yes.
Yes, it is a positive slope. So when the slope of the tangent line to the graph of a function is positive, then the function, you see, it's increasing. Let's look at another piece here. If at this point I draw the tangent, the slope of this tangent, is it still positive?
Yes.
Yes, it's still positive. Which of these two has a higher slope, the first one or the second one? Which of these two is harder to walk on? Is this one harder to walk on, or this one is harder to walk on?
The second one.
The second one. Or the first one? The second or the first? Yes, the first, because the first has this slope, the second one has this slope. It's much harder to go uphill this way on the first one than go uphill for this one. So notice that here, the slope is higher than here. Is that clear? Everyone sees that? Yes?
Yes.
Now, would you agree that this is something called local, also called relative? It doesn't matter which one you use. Max or min?
Max.
Absolutely. Now, at this point, I have to draw the tangent. What is the slope of the tangent at this point?
0.
Excellent. So the slope here is 0. Perfect. So here's what we noticed so far. If the derivative, what do you mean by the derivative? Well, the slope of the tangent at these points is the derivative, as we just did. Your example eased our discussion, really helped me discuss this. It was perfect. How do I determine the slope of the tangent? By finding the derivative at that point. So the derivative here is positive, and big. The derivative here is positive but smaller. The derivative here is 0. That's the slope of the tangent line. Okay, stay with me and we'll analyze this in a minute. So let's look at this point. Let me use a different color now. At this point, I'm going to draw the tangent. What type of tangent is this? What is the slope, I meant to say?
Negative.
Yes. Look what the function is doing. Is it decreasing or increasing?
Decreasing.
Yes. So far for now, what we know is this. When the slope of the tangent line is positive, the function is increasing. When the slope of the tangent line is negative, the function is decreasing. When the slope of the tangent line is 0, that's a special point. In this particular case, it was a maximum. What about here? If I draw the tangent line, or the derivative, in other words, I get again the slope equals 0. In this particular case, because the function decreases and then obviously increases, what type of point is this? It's called local or relative, but what?
Minimal.
Yes. So what do we learn from the first derivative? A lot about the function. If the first derivative is positive, what does the function do?
Increase.
Yes. Now, from our graph, if the first derivative is negative, what does the function do? If you want an arrow here.
Decrease.
Yes. Furthermore, notice the sequence of signs. If the derivative is positive, then it is 0, and then it is negative. Positive, then 0, and then negative. What type of point are we looking at? F has a relative what?
Maximum.
Yes. In other words, this situation. Positive derivative, 0 derivative, negative derivative. Positive, 0, negative. A maximum. Leave some space here. I'm going to move on to the next option. What about negative, 0, positive? Negative slope or negative tangent, 0 tangent or derivative, positive slope or derivative. What will the function have?
Minimum.
Yes. Now, there's the reason why I said leave some room here and some room here. I will come back to this in a blink. I need another graph, and I don't want to put it here. Okay. Do you remember when we looked at functions like these? What did we say about these functions? Are they continuous?
Yes.
Continuous. This one has a cusp, like between two teeth, and this one has a corner. And we also had something like this. This was also continuous. Let's come back to these two. This is a different story, but let's come back to these two. I just wanted to present all three situations we discussed. Okay, this one, it's continuous. Is it differentiable?
No.
No, not differentiable. But now if you look at this graph, does this function have a relative minimum at this point? Before you say anything? Yes. Yes, this is a relative minimum. Decreases, 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 increases. So this is a relative minimum. Is this a relative minimum? And is the function not differentiable? Of course. What does it mean? It doesn't have a derivative here. The derivative is undefined. Here, f prime is undefined. Here, f prime of x undefined. But it has a minimum. Can I have this situation? Yes. It's still a cusp. It's still continuous. It's still not differentiable. But this, in this particular case, it has a relative what?
Max.
Very good. So the same situation here, I can make it this way. This is a totally different situation. It's continuous, not differentiable. But this situation is not part of these two because there is no relative max or min. This is not the same category. So that's why I wanted to come back here. See the derivative, negative, negative, minimum, and then positive, positive, positive. Negative, undefined for the derivative, and positive. Negative derivative, undefined derivative, positive derivative. What type of point is this? Negative slope, decreasing function, and then increasing function, positive slope for the derivative, or the slope of the
Minimum.
Yes. So what we learn from here is if the derivative is 0 or it is undefined, if we have this sign change, the function will have a relative minimum. What do you think I should write here? And I would write it.
Positive, undefined, negative,
Awesome.
relative max.
So a function can have a relative max if its derivative is 0 and it's or undefined, and the sequence of sign is always this: positive 0 undefined negative, or positive undefined negative. This will always be a relative max. So in summary, what is the first derivative giving us? 3 things. It tells us whether the function is increasing through its sign. It tells us if the function is decreasing through its sign. And it tells us if the function has a max or a min. That's the reason why we learned in the previous chapter how to differentiate functions, because we wanted to find their max and min, and when the function is increasing or decreasing. And these come from the first derivative. That's why the first derivative is so important. Not just that it gives us the slope of the tangent line at a particular point, but furthermore, it tells us when the function is increasing, meaning the derivative is positive, when the function is decreasing, meaning the derivative is negative, and where the function has a max or a min. Now, if I look at f of x equals x cubed, remember the graph? We discussed those important graphs. So this is x to the third. Just